हेलो अस्सलाम वालेकुम ये अभी हम अब्दुल्ला can you hear me मारूफ ठीक है अच्छा we this one ये कौन सा पेपर करने जा रहे हैं we are trying to do October November 2021 this is question paper 2 we'll try and complete this so we're going to try and do this paper इस क्लास के अंदर तो अच्छा इसके अंदर अब ये कि we're going to start with the first question which is कि explain why HI has a higher boiling point than HCl and HBr. So if I just Google quickly the boiling points of hydrogen halides, बल्कि यहाँ पे notes के अंदर ही देख लेते हैं कि the boiling points of our hydrogen halides. अगर if you go to group 17, ठीक है, तो मैं एक सेकंड जल्दी से group 17 खोलूं. So this one, the boiling points of hydrogen halides. If you can see on the screen. So यहाँ पे what happens is that the HF has a very high boiling point and that is because it's got hydrogen bonds. And then subsequently the boiling points, they decrease because these molecules are less polar. But HI has greater boiling points because, why? Because it's got van der Waals forces. It's a bigger molecule compared to HCl and HBr. So you get a lot of this question. यहाँ पे the explanation is also provided that HF has hydrogen bonds. What happens is the polarity of HI is lesser, so it's going to have weaker permanent dipoles, but it's a bigger molecule, so it's going to have more permanent, more van der Waals forces, more temporary dipole, induced dipole attractive forces. So this is what you're going to quote over here is that it's a bigger molecule. It's got more electrons. So which is why there's going to be more temporary dipole induced dipole interaction. Induced dipole or van der Waals forces. So that's for the first one. Now the bar chart shows the boiling points of HCl, HBr, and HI. The boiling points of HF is not shown. So we just draw on the bar chart to predict the boiling point of HF. Explain your answer. So the boiling point is going to be pretty high. So it's going to be somewhere. It's going to be somewhere over here in this particular range. And explain your answer. So it's going to be higher. So we did get 1 mark for sketching this. That's the boiling point. You can draw the bar chart over here, and it's going to be higher compared to HCl. Why? Because it's got hydrogen bonds. You're going to write a statement on that. It has hydrogen bonds, which are stronger intermolecular forces, or which are very strong. That's what you're going to write. The next part is define the term standard enthalpy change of formation. So what is formation? It is like if I want to write the formation of HI, 1 mole of HI is going to be formed from its constituent elements. HI is a gas. Everything has to be under standard conditions. So the elements would be H2 and the elements need to be in the standard conditions as well. And you've got I2, which is going to be a solid. This is going to be half and this is going to be half as well. So the definition is, and you have to remember the definition. So it's the energy that is, so it's the energy change that is, it could be positive and it could be negative as well. So it's the energy change that is associated with when 1 mole of a substance is formed from its constituent. So when 1 mole of a substance is formed from its constituent elements or from its elements which are in their standard states. And Since you're talking about standard, you would also have to quote it's measured under standard. It's measured under standard conditions. Now, the next part of the question is it's a KP question. You're being asked construct an expression for the equilibrium constant KP for the reaction of H2 and I2 to form HI. So KP is it's the pressure due to the products and divided by the pressure due to the reactants. So it's going to be pressure due to HI, and that's going to be squared, and uh, and it's going to be divided by the pressure due to H2 multiplied by the pressure that's due to I2. They've kind of simplified the question. The equilibrium partial pressure. I need to open the marking scheme as well, especially to check the calculation. So, Abdullah, make sure you have one open. Ah, okay, we can do that. And so here's the MS for the same paper as well. W21 MS 22. So this one over here. So, anyways, he's saying calculate the value of KP. So pretty easy. Everything is provided. You just have to plug in the value. So I'm going to do it over here. It's going to be, make sure you show your workings properly. So it's eight pressure due to H2, pressure due to I2, and pressure due to HI. So it's going to be 4800, and that's going to be squared, and it's going to be divided by uh, 895 and multiplied by 895 again. So if you do this on your calculator, and let me open the calculator very quickly, and make sure even in your practice sessions, practice with your calculator. So it's going to be 4800, and that's going to be squared. I mean, you should be very familiar with your calculator divided by. Uh, put, put things in brackets. Make sure you tell your calculator clearly what you're trying to do. Even if you're doing 4800 squares, put brackets around it. So there is no confusion. So it's going to be 895. At least on your calculator, there should be no confusion. Uh, so what I'm getting is I'm getting 28.763, but since the values are up till three significant figures, my answer will be rounded off to three significant figures, and it's going to be 28.7 pascals. That is actually, there's not going to be any unit. There wouldn't be any units for this. Why? Because the units are going to get cancelled out. Because over here it's Pascal squared divided by Pascals into Pascals. So all the units are going to get cancelled out. So it's just going to be 28.7, and it's not going to have any specific, it's going to be dimensionless. State how the value of Kp would change if at all the reaction was carried out at 100 degrees centigrade. So you're decreasing temperature. When you now now temperature is one thing where the value of the constant equilibrium constant Kp and Kc, they both change. So you're decreasing temperature, and when you decrease temperature, what should happen is that the exothermic reaction, according to the Lee-Chatelier principle, it should be favored. So the exothermic must be favored in this case. But so we have to go back and we have to figure out which one is the exothermic reaction. They did give us delta H for this, the enthalpy of formation, which was endothermic plus 26.5. So, and that was delta HF of HI gas, and it came out to be 26.5. Now there's an issue over here, which is that delta HI, the iodine was a solid. Over here, the problem is that, uh, and they've actually given this. You don't have to calculate the enthalpy change. The reaction is reversible, and he says no, it's still not given. Uh, so state how the value of Kp would change if at all if the reaction was carried out at 100 degrees centigrade rather than 200 degrees centigrade. So what you can do over here is you can quickly figure out what the enthalpy change is. Because we don't know what the enthalpy change is. The enthalpy of formation is given, but I can't really rely on that because in the enthalpy of formation of HI, the iodine has to be in its standard state. It should be a solid, but over here it's not a solid. So what I'm going to do is I'm just going to quickly figure out what the enthalpy change is based on the data booklet. I mean, you can do that. It's simply bonds broken minus, because everything uh, is gaseous. So I can use this bonds broken minus bonds formed, and I can I'll try and calculate this enthalpy change. So which bonds are broken? I'm breaking the HH bond and I'm breaking the II bond. And which bonds are being formed? They're basically two HI bonds that are being, two of them. They are getting formed. So we can just quickly open the data booklet. Let me just have the data booklet in front of me. Now this one, no, it's still not there. I just have my data booklet over here. It's HH breaking HH. That's 436. So let's put that. HH is 436. That's going to be endothermic. I need to break the II bond as well. So in the data booklet, the II bond is 151. That's also there. So that's 151, and then I'm forming two HI bonds. This is going to be exothermic. Bond formation is exothermic. So HI is 299. That's given over here as well. Let's put that in. That's minus 299 times 2. So I just want to figure out what the enthalpy change is. I just want to be sure. So HH on my calculator is going to be 436. Abdullah Mark, can you try and do this? It's 436 plus 151, and then it's minus 299 multiplied by 2, and I'm getting minus 11. So the enthalpy change I'm getting is minus 11. So the enthalpy change for this reaction in the forward direction, it's minus 11. It's exothermic. So the forward reaction is exo. That means the backward reaction is the one that's going to be endo. Um, so although this might be an unnecessary, because it still came out to be exothermic, but I wasn't. It's actually coming out to be exothermic. So it's this one was actually endothermic, where iodine was taken as a solid in the enthalpy change of formation. But if you're doing this at gaseous substances, then it's coming out to be exothermic. So over here, what will happen? What did I tell you? That decreasing temperature would favor the exothermic reaction, which is in this case is going to be the forward reaction. So if it's the forward reaction, there's going to be more of HI that's going to be produced. So more forward reaction, or what you can write is that the equilibrium, it's going to favor the forward reaction. And since it's favoring the forward reaction, which means uh, Kp is the product pressure divided by the reactant pressure, or pressure due to reactant. So if you have more products, Kp is going to have a higher or a larger value. So I'm just going to double check this one. Option one is, so they've given both of them. It's actually uh, option one. So they've actually, if you look at the marking scheme, they've actually given both options, because the confusion over here was that the enthalpy of formation could not have been used, because enthalpy of formation is for solid iodine. The element has to be in under standard conditions. So I decided not to use this value, especially for the equilibrium that followed. That was endothermic. I calculated my own enthalpy change using my bond energies that are given in the data booklet, and I figured out that's actually coming out to be exothermic, because over here iodine is a gas. So I figured out if it's exothermic and you're decreasing temperature, then the forward reaction would be favored. Now, the market scheme has allowed both options, but the option two that we selected And maybe the reason they allowed both options was because a lot of students actually didn't get the question, so which is why they ended up allowing it. So which realized that enthalpy of reaction is in fact exothermic. So we did figure that out using bond energy data in the data booklet. And so Kp should increase. Exothermic means the favors formation of products. You get more products. uh, so partial pressure. So we did write this one. Did we get mark number 2 for this? We did get Kp increases, and we did write that there's more formation or equilibrium shifts to the right. We did quote that equilibrium favors forward reaction. So Kp is going to. I mean, you could have been clearer on this that the partial pressure of the products would increase, or the partial pressure of HI would be higher. So that's it for this one. The next one is, okay, so now let's focus on the next one. So he's saying HI reacts with oxygen to form iodine in water. Construct an equation of HI with oxygen. So just to make the equation, what they're telling you. So HI reacts with oxygen, and it ends up forming iodine in water. So that's I2 plus H2O. And to balance this, you would have to have 2HI, and there's going to be half O2, right? That would kind of balance things up. Yep, it looks fine. Explain with reference to the oxidation number why the reaction is a redox reaction. So I mean, just quote the oxidation number. Oxygen goes from 0 to -2. So oxygen oxidation number changes from 0, because in elemental form it's 0, from 0 to -2. So which means it got reduced. So that means reduction happened. And you can quote the other one, which is that who's getting oxidized? Iodine goes from -1 to 0. So iodine, the oxidation number changes from, -1 to 0. So this is oxidation. So with reference to oxidation, so it's a redox reaction. Both things are happening. State the change in pressure that would occur when 2 moles of iodine fully react with 1 mole of N2H4 in a sealed container at constant temperature. Explain your answer. So the change in pressure when 2 moles of iodine fully reacts with 1 mole of N2H4. So 2 moles of iodine fully react with 1 mole of N2H4. So what they're going to end up doing is they're going to produce 4 moles of this, and they would produce 1 mole of this. So if they fully react, which means these two completely react and they produce this, so the amount of moles of gas would increase. Products have more moles of gas. So they have more moles of gas. So which means more gas is produced. And if more gas is produced, uh, it's a constant temperature. So you have more gas. You're going to talk about collisions of particles. So there's going to be more frequent collisions with the walls of the container, and the pressure would increase. And as a result, the pressure would increase. So that's about this one, and we can so pressure number increase into or pressure is directly proportional to the number of moles. Pressure increases, so we kind of said that the moles are increasing. So the pressure is increasing. So I think we should get this mark as well. uh, More gas is produced, so more frequent collisions with balls, and the pressure would increase. So kind of it means that if you have more moles of gas, so I think we will get the mark for that. And moving to the next one, you have to draw the dot and cross diagram of Pi3. So that's phosphorus has 5 electrons, iodine has 7, and you just have to phosphorus has 5, so it makes 3 bonds, and 2 electrons are left. And iodine has 7, it shares only 1 electron. So 6 electrons of iodine are left. So this iodine as well, and this iodine over here will also have 6 electrons. It will also have 6 electrons. Name the type of reaction step 2. So what type is that? That is hydrolysis. Remember, uh, this one is hydrolysis. How did we know that this is hydrolysis? Because we studied it in in inorganic. Like if you open period 3, if this opens up, ठीक है, Abdullah, make sure you open those notes. So this one, if you look at this one, there's hydrolysis of chlorides. Now, the reaction over here, and let me make this bigger. So PCl3, we did study a reaction of PCl3 with water, which is kind of similar. It's H3PO3 plus HCl. So all these chlorides, the reaction with water, it's known as hydrolysis. This strongly hydrolysis. This is strong hydrolysis. So PCl3 with water. So Pi3 is doing exactly, you're getting the same exact equation over here as well. It's H3PO3 plus 3HI. The only thing is the Cl has been changed to I. So the reaction is still hydrolysis. It's the molecule breaking down in the presence of water. Now, H3PO3 and HI are strong Bronsted-Lowry acids. Give the meaning of the term Bronsted-Lowry acids. It's basically a proton. I mean, an acid is a Bronsted-Lowry acid is a proton donor. And strong means that it ionizes fully. Like it doesn't do that partially. So it's a Bronsted-Lowry acid that fully ionizes. Uh, that's what strong means, and proton donor, that's what an acid is. Give the formula of the conjugate base of H3PO3. So whenever you have an acid, the H3PO3 would produce H plus one ions. So it's going to produce or release H plus one ions. So that's how it acts as an acid. So let's assume that it releases one H plus one ion. So what's left is H2 PO3 with a charge of -1. So this is acting as an acid. Why? Because it's obviously losing an H plus one ion. In the reverse direction, it's going to gain H plus one ion. So this thing over here will be acting as the base, and that's in the reverse direction. That's known as a conjugate base. So it's acting as the base, so it will gain those H plus one ions back. So that's your conjugate base in this case, and we can double check that. It's H2PO3 -1. That's the conjugate base. Now, the next part of the question is we've got HI reacts with propene, and you have just 1 second. Okay. I said now the next part of the question is you've got HI gas with propene, and it reacts to form a mixture of 1 idopropane and 2 idopropane. Identify which of these is the major product. So that's about Markovnikov's rule, which is he's saying identify which one is the major product of the reaction, and you have to explain as well. So you have to give an explanation as well. So first thing is for unsymmetric alkenes, the rule is that when electrophilic addition happens, so let's assume that an HI molecule is coming in The H part is positive, the I part is slightly negative, and the H is getting attracted to the double bond. So that's how the mechanism of electrophilic addition happens. The I gets repelled. That's the first step. So the H will either bond with this carbon atom or with this carbon atom. The rule is that the H likes to bond with the carbon that's already bonded to more H atoms. So this carbon is already bonded to two H atoms directly. So it's going to bond with this one. So the carbocation or the product that's going to be formed is going to be this one. That it's going to be CH3C. The H, I mean that's your molecule. So the H would bond with this carbon atom, and the I would go with this one. So the major product or the more likely product for this reaction is going to be 2-iodopropane. That's the one. So that gives you 1 mark. You figured out what the major product is, and the explanation for that is that when this reaction happens, especially this one, a carbocation is going to be formed, and it's going to have H bonding to this one, and this carbocation would be formed. Now, this carbocation is a 2-degree carbocation, and 2-degree carbocations are more stable because they have more electron donating alkyl chains. So the other part of the explanation would be that it's got a 2-degree carbocation. Why do I call it a 2-degree carbocation? Because this carbon is bonded to two carbon chains, so it's like a secondary carbocation. So it's got two carbocation. It's a 2-degree carbocation. So alkyl chains have electron donating effect, which makes it stable. So you're going to write that this particular carbocation is more stable. The major product has a 2-degree carbocation. What that basically means is that when the H takes electrons from the double bond, the carbon is going to have a smaller positive charge. Why? Because it's surrounded by carbon chains on both sides. So it's got a lot of electrons in its neighborhood. So so the carbocation has a lot of electrons around it. So the electrons would partially neutralize this positive charge. It's going to pull electrons, 9 electrons on this side, 9 electrons on this side. So it's going to pull some of the electrons, and the positive charge will get neutralized. So which is why the positive charge is smaller. That's the reason why the H is able to steal electrons. Because if the positive charge had been bigger in size, the H would not have been able to take electrons from the double bond, because the H was stealing electrons from the double bond. So the reason the H was able to steal electrons from this double bond was that the carbocation that was formed, the 2-degree carbocation, had a much smaller positive charge density. Why? Because it's surrounded by alkyl chains, which are electron donating. But you just need to know a simple fact, which is every time that a 2-degree carbocation or a 3-degree carbocation is more stable, because you've got alkyl chains which have electron donating effect. I'll just quickly check the. I mean, that's about it. So 2-iodopropane, uh, uh, and they're saying that it's got a stable carbocation intermediate. Why? Because it's got two alkyl chains, and alkyl chains have more electron donating. I mean, positive inductive effect is, it basically means the same thing, that it's got more electron donating effect. So positive inductive effect is the same thing as the electron donating effect. So you had to mention the alkyl chain. So we did that. The carbocation was more stable. So we got both marks for that. So now the next part is about the mechanism. So you just have to write the mechanism. So you have a positive H. All you have to do is make one arrow, and the iodine electrons are getting repelled. The carbocation would be formed. So it's going to be CH3. You're going to have the double bond would go away. It's going to be H. Uh, and there's another H. Anyway, so the H from HI is going to bond with the carbon that's already bonded to more H atoms. And in the next step, a carbocation would be formed, and then the I minus one with its extra electrons will get attracted to the positive carbocation, and eventually you'll get the whole molecule. So that's about it for this one. Now the next part is, let's do this one now. Table gives physical data for some of the PhD elements. Uh, and the first question was a big question. It's like it's 26 mark question. So that's a big question because we're on the seventh page. Now, bonding present in element and the ionization energy is the oxidation number. So it's I think it's all about PhD elements. Sodium. I mean, this is sodium. I'm going to write the element sodium. I've got magnesium. I've got aluminium. I've got silicon, phosphorus, sulfur, and chlorine. So I've got all these elements, and the maximum oxidation number is given. So complete the row in the table labeled bonding present in element. C equals covalent, I equals ionic, M equals metallic. So that's the first thing. So bonding present in the element. So remember, remember the bonding and the molecular structures as well. I'll just go through that in the notes as well. Like if you just open this. So over here, you'll in period C. This is all about the bonding in period C elements. The first three are metallic: sodium, magnesium, and aluminium. Sodium has a very low melting point. It's because it's got the size of the ion is bigger, so it's got a metallic lattice. It's which is why bigger ions, the electrons are further away, the charge density is lesser, and they're lesser delocalized electrons. So which is why the attraction between the electrons and the metallic ions, it's not that large. In aluminium, it's much stronger. So the first thing, a metallic. Silicon is a giant covalent structure, must be given over here. Silicon is a giant covalent structure similar to diamond. It's got a very high melting point. And then you have the last four, which are chlorine, phosphorus, sulfur, and argon. Argon doesn't even form any bonds. It's a monoatomic molecule. Sulfur is S8. Phosphorus is P4, Cl is Cl2. So this one is. So I'm just going to write the first three are metallic. Um, there's no option for giant covalent, so I'm going to write 14 as just covalent, and these are covalent as well, but these are simple covalent: 15, 16, 17. This one is a giant covalent. Explain the difference between the first ionization energy of the elements with atomic number 11 and 17. So what happens to ionization energies across the period? Across the period, they increase. The general trend is they increase across the period. And there's the minor dips. I mean, this is what happens if I just quickly. So this is the general trend across the period. Like if you see this graph over here, the general trend Na to Ar, that's increasing. There would be dips at aluminium and sulfur, group 3 and group 6, but the general trend is they increase. And what's the reason for that increase across the period? You have the same number of shells. The protons increase. So the protons and the nuclear charge increases. So obviously, if you have more protons, the electrons are more strongly attracted. The distance gradually decreases across the period. It's a 2 mark question, slightly decreases. And what else happens across the period? You've got distance slightly decreases, and the third one is that as you move across the period, what happens is that as you move across the period, what happens is your shielding remains constant. You have the same number of shells. So because of the above factors, there's more attraction between the nucleus and the electron. And remember to write this last point: more attraction between nucleus and electrons. So it's a 2 mark question, so you'll just get marks for 2 of the points, but we'll answer that fully as possible. So so the answer to that was nuclear charge increases. They actually gave you three. I mean, I had to score 3 points. 3 points for two, so basically 3 points. So nuclear charge increases, similar shielding, and the last one was the overall effect in terms of greater nuclear attraction. Or electrons are attracted more strongly to the nucleus. That's remember to make sure you write this point whenever you answer this. Now, the other part is explain the difference between the first ionization energies of the elements with atomic number 15 and 16. So he's talking about this one. He's talking about the dip over here. What happens? What goes wrong between phosphorus and sulfur? Why is there a dip? So the answer to that is phosphorus's electronic configuration. The outer shell is 3s2, and it's 3px1, 3py1, and 3p. Z is also 1. Sulfur is 16 electrons, so the outer electronic configuration is 3px2, 3py1, and 3pz1. Now, you're going to talk about the first thing is you're going to quote these electronic configurations, or what you can state is that in sulfur the electron is removed from a paired p subshell. So in S, electron is removed. So it's removed from a paired p orbital, and since it's removed from a paired p orbital uh, due to spin pair repulsion, so due to spin pair repulsion, the two electrons repelling each other, it becomes easier to remove electrons. While in the other one, in phosphorus, you're going to quote the phosphorus one as well. So in phosphorus, on the other hand, electron is removed from a half-filled orbital, p orbital. So from a half-filled p orbital, and there is no spin pair repulsion. You should quote that as well. No spin pair repulsion for that. So so spin pair repulsion, that's 1 mark. Electron repulsion describes the location of the electron pair in the 3p orbital which repel each other. So you have to describe the location as well. So we did that as well. Now the next part is complete the row maximum oxidation number. So maximum oxidation number of sulfur is usually +6, like in SO3. Phosphorus is +5, like in PCl5. Silicon +4 usually. These are metals. Aluminium is +3. You've got magnesium, which is +2, and you've got Na, which is +1. Moving to the next one, you have complete the row. Explain the variation in anionic radius of the elements with atomic number 14 to 17. So what happens is for anions, like if you have phosphorus, you have sulfur, and you have chlorine. This is -3, this is -2, and this is -1. All of these are isoelectronic, which means that they actually have the same number of electrons because phosphorus is supposed to have 15, sulfur is supposed to have 16, and chlorine is supposed to have 17 electrons. But with the negative charge, they now have 18 electrons. This one also has 18 electrons, and this one also has 18 electrons. So you're going to state that they have the same number of shells and the same number of electrons, but this is going to be smaller. Actually, sorry, this is going to be bigger. So this one over here is going to be bigger in size. I'm talking about phosphorus over here. It's going to be bigger in size, and Cl is the one that's going to be smaller in size. Why? Because the number of protons. You have the same number of electrons, but the protons are increasing. So which is why, relatively speaking, 17 protons are going to attract the 18 electrons more strongly, while 15 protons will not be attracting those 18 electrons that strongly. So remember this, and so they have the same number of electrons, that's isoelectronic, and the increasing number of protons. That's those are your explanations for that. Now the next part is use the axis sketch the graph to show the trend in melting points of the elements atomic number 11 to 17. So we just did describe that over here. You just have to code this 11 to 17. So that's sodium, that's got a low melting point, magnesium, and then you've got aluminium. So sodium is going to be somewhere at the bottom. Sodium has a melting point of 98. Magnesium and aluminium will have a relatively higher melting points compared to sodium. Next part is you've got this thing. He says complete the table by predicting values for the missing data. So I don't know what the. I mean, you just have to. Yeah, you just have to match the trends. So what's happening? Density is increasing down the group. So 5 points. I'm just going to write 4 over here. Uh, and again, the trend is decreasing. So the boiling point is decreasing. So let's take this as 1900. And the cation radius. We can actually go in and look at the periodic table about the cation radius. I don't know if gallium is given, but uh, complete the. So the question is more about predicting. So we don't actually have to write the actual value. So if I want to predict this one, this would be, let's say, 0.65. So we'll just let me just quickly check what kind of predictions were they looking for. So anything between 2.5 to 5 was acceptable. So ours case is that's within that range. This one as well, I think that's they're going to say something like this. We're getting 1900. So that was also acceptable. The other one we talked about 0.6065. So that's also kind of acceptable. So also, and I forgot to write a zero over here. That's one thing that's not there. So avoid silly mistakes at all cost. You're going to lose unnecessary marks if you do that. Now, indium and aluminium are metals in group 13 of the periodic table. Indium has very similar chemical properties to aluminium. Indium reacts vigorously with hydrochloric acid to form a colorless gas and a salt in solution. Indium oxide is amphoteric. Gaseous indium has this formula. The molecule contains coordinate bonds. Identify the formula of the salt formed when indium reacts with hydrochloric acid. So, so indium and aluminium are so kind of. I mean, they're in group 13. So I'm assuming the first thing is I need to assume what the formula of the what is the symbol of indium. Uh, so we look at the periodic table, and it's in group 13. It is iron, which I was thinking it's iron. So group 13, that is iron. That's indium. And he says it reacts vigorously with hydrochloric acid, so that's HCl. And it's going to form iron Cl3. Iron is going to be +3. So if reacts it to form a colorless gas, that's going to be H2. We just have to figure out the formula of the salt, not the whole equation. And construct an equation for the reaction of iron 2O3 with excess NOH. So it's the same as aluminium because whenever you get a question like this, and where they say that they have similar chemical properties to aluminium, so they're basically talking about aluminium. They're not actually even talking about indium. So what happens when IN2O3 reacts with NOH? This is aluminium. Remember, aluminium is amphoteric. Oxide is amphoteric. So the reactions of aluminium are also quoted over here, which you have to memorize. This one amphoteric. That if Al2O3 reacts with NOH, it's going to form NaLO2 plus it's going to form H2O. So that's what's going to happen, or NaLOH4 as well. A lot of equations for this reaction are acceptable. So it's going to form NaAl. Instead of Al, I'm going to write iron OH4 plus H2O. And all we need to do is we need to kind of balance this. So how do you balance this? It's first thing is there's going to be two of them. So that's 8 hydrogens here. That is 8, yes, and two over there as well. So So how do you balance this? This 2 NaOH, 2 NaOH, so there's got to be 2 NaOH. It would be a lot easier if we, instead of OH4, if I use the other one, Al, NaAlO2, if I use this equation. So 2Na, and I think the equation would be balanced. 2H's, that's 2H's. The oxygens are 3 plus 2 of that's 5. So over here I have 4 oxygens. So it's already balanced. And that is going to be one of the acceptable equations. They're going for NaOH4, but I'm pretty sure that's acceptable. You get multiple equations with Al2O3 reacting with NaOH. So the equation that we wrote is definitely going to be acceptable as well. And the next part is they're saying that the diagram is draw the diagram that clearly shows the bonding that is present in iron 2Br6. So the gaseous, now again it's like you need to know the dative that dative bonding happens. Again, it's part of inorganic. You should know that dative bonding happens with like if you with AlCl3. In our case, we have iron and we've got Br. So the group 3 element has been replaced by iron, and over there it's been replaced by bromine. So it's going to be a similar type of dative bonding. You just have to show that. So we're going to do just that. It's going to be iron, and you've got Br, and there is another iron, and you've got Br. Now the lone pairs on Br would form a dative bond with iron. The lone pairs on this Br would also form a dative bond with this iron over here. So it's going to be iron 2Br6, and that's going to be your dimer. It's known as a dimer. That two iron Br3 molecules have joined up. Now this one, we're on the hopefully on the last question. Uh, this one over here is ठीक है अब्दुल्ला ठीक है ये कर लेते हैं फिर उसके बाद खत्म कर लेते हैं. We've got we have to name compound T. So how do you name compound T? That's 1, 2, 3, 4. That's the longest chain. So that's bute. Ene. There's a double bond. This is carbon number 1, carbon number 2, carbon number 3, and carbon number 4. So that's the double bond is on the second one. So it's butene, and there are two carbon branches, this one and this one. So there's one carbon atom branch over here. That's a methyl branch. There's another methyl branch. One is at 2 and the other one, so it's a dimethyl. You've got two methyl branches. One is at position number 2, the other one is at position number 3. So that's the name of the molecule. Draw the skeletal formula of the structural isomer of T that shows cis-trans isomerism. So we've got a total of 6 carbon atoms. So we need to, so for cis-trans geometrical isomers, what you need is you need a double bond, and you need different groups on each side. So that's how. So remember, I've got 6 carbon atoms. I need to arrange it in this way. Just hold on 1 second. Okay, this one. So sorry. So we've got a double bond, and I have to make cis trans. So both sides over here would be different. Both sides over here should be different. So what I can do is I've got 6 carbon atoms. What I can do is I can put an H over here, and on this side I can put a carbon atom, right? And on this side it should be different as well. I put an H over here, and I've got 3 carbon atoms left. So I'm going to put all those 3 carbon atoms on this side. So this would be 3 H's, CH3. This would be 2 H's, 2 H's, and 3 H's. So that is a cis version of this molecule. So I've drawn an isomer of a molecule having 6 carbon atoms that's got a double bond, and it should so use this saying draw the skeletal formula of this. So that's 1, 2, 3, 4, 5, 6 carbon atoms. So that's 1, 2, 3. You've got 4. You've got 5. And you've got, let me just count, 1, 2, 3, 4, 5. And then there is a sixth carbon atom. The double bond is on the fourth and the fifth. So there's a double bond right over here. And so you've got a double bond over here. So that's my skeletal formula. Now each carbon atom has a sigma bond, at least one carbon atom. Draw on the diagram, show the orbitals that are present. How do you make a pi bond? The pi bond is that this carbon has a p orbital, spare p orbital. This carbon also has a spare p orbital, and they would start to overlap above and below. So you can shade, so the electrons of this extra p orbital, they would overlap, and there's going to be an electron cloud that's going to be above and below. So on the diagrams, show the orbitals overlapping. So that's how you show pi bonds. And state the hybridization of the two carbon atoms. Whenever you have double bonds, the carbon is sp, it's sp2. What is sp2? When carbon is just bonded to three atoms, that is, it's bonded to three atoms, so it's making three normal bonds, and the fourth electron of carbon in its outer shell is unused, and that is involved in pi bonding. Now, the next part is a reaction scheme. Starting with T is shown. The reaction 2 occurs in the presence of a catalyst. Knowledge of the mechanism of this reaction is not required. Give the reagents and conditions for reaction number 1. So you've got an alkene and it's turning into a diol. So for this, I'm just going to quickly open the chart for organic. This is basically mild oxidation. So the organic revision chart, make sure you have this with you. And make sure you memorize all of this. So here is the revision chart on your screen now. So what happens? You have a double bond. Double bonds undergo two types of oxidations. You have mild oxidation. You've got mild oxidation is cold dilute alkaline KMNO4, and that results in the formation of diols. So in our case, this over here is mild oxidation. So it's going to be cold dilute. So mild conditions, acidified KMNO4. So that is mild oxidation. Now the other part is state and explain how 2,4-DNPH can be used to detect the presence of V as a product of reaction 2. So V, 2,4-DNPH. What does 2,4-DNPH do? It's a test for carbonyl compounds. That's also given in this chart over here. Whenever you have ketones and you've got aldehydes, you get an orange precipitate with 2,4-DNPH. 2,4. So that's, they're going to give an orange precipitate. That's about it. So not sure what the second mark is for. So the second one would be probably for the ketone. It's got a ketone group. You're going to mention that. So there's a ketone group in V, and you're going to mention that this ketone group gives an, you're going to write a proper statement, orange precipitate, or it's going to give a positive result with 2,4-DNPH. So they're definitely not looking for the equation in this reaction. So I'll just quickly check with the MS as well. So we're dealing with this one. So it's orange precipitate has a carbonyl group. That's it. Ketone group is a carbonyl group. So that is correct as well. Now the next part is the progress of reaction number 2 can be monitored by infrared spectroscopy. Reaction number 2. So absorption caused by OH bonds is always present because of water is used as a solvent. So we're going to discount the OH bonds because they're always present. So we're not going to think about the OH bonds because he's saying they're always present. So you can't, if something is present before a reaction and something is present after a reaction, that doesn't make any difference. So identify 2 absorptions and the bonds responsible for these absorptions whose appearance will change significantly during this reaction. So let's go back. Here's the reaction. So which bonds are present? Like once reaction number 2 happens, you got a C double bond O now. So the C double bond O starts appearing in the molecule. And before the reaction, we're going to ignore the OH bond, but there is a C single O bond, right? So before the reaction, the carbon and the O over here, they have a single bond O, and that turns into a C double bond O. So they're basically two bonds. The C single O would be disappearing, and the C double bond O would be appearing. So you open the data booklet. Now the chart would be given to you. Go to the infrared spectrum, wherever that is. That's over here, and you would notice that. So you would notice that you've got a strong absorption at 1040 and 30, and this absorption would disappear during the reaction. It would disappear. Why? Because this bond is going to it's not going to be in the product, so it's going to disappear. So that's one. So 1040 to whatever the value was, let me just quickly 1300. C single bond O absorption would disappear. So this one would disappear. And the other one is what will appear is the double bond O. It's a ketone one. So where's the data booklet? So the ketone 16, 17, 17, 40. You have to be very specific. 16, let me just open that again. So it's this one. The C double bond O is going to appear. So this one would appear. So C double bond O, you're going to code that. Whatever 16, 17 to 1740. So initially it wasn't there, but now in the product it's going to be there. So absorption would appear. So these two would change significantly. So that's the answer to this one. Now the next part is V is used as in a wide range of organic reactions. Some reactions of V are shown. So you've got V, and what would you observe in reaction number 3? So this one, alkaline aqueous iodine. That's an iodoform test. That is this test over here. Like if you iodoform test is over here. Then whenever you have a CH3 which is right next to a C double bond O, the CH3 will break off and it will turn into a yellow precipitate of CHI3. And the other carbon will just turn into a salt of the carboxylic acid. So this is exactly what's happening. If you look carefully, you had a CH3 over here, and this CH3 it was right next to a C double bond O, so it broke off. And when it broke off, it would form a CHI3 yellow precipitate. So that's the first one. We're going to write yellow precipitate. Now, what's the next one? Identify which of the reactants is reduced in this reaction. So, which reaction? You think reaction 3 is a redox reaction. So which of the reactants are getting reduced? It's iodine that's reduced. Why? Because iodine was an element and now it's CHI3. In CHI3, iodine has a charge of it's an oxidation state of -1, so it's the one that's getting reduced. The other part of the molecule is actually getting oxidized. Like if I one second. So if I just go back and have a look at this, I'll explain the oxidation part. This carbon over here, it turns into a carboxylic acid, basically double bond O and OH. So this carbon will turn into a carboxylic acid. It's going to get oxidized. So this is an oxidation reaction. It's written over here as well. For the carbon, this part, it's the reduction part. So use H to represent an atom of hydrogen. Okay, hydrogen from NaBH4. He's saying construct an equation for reaction number 4. So reaction number 4 is this one. So what is X? It's you have to figure out the number of carbon atoms. That's 1, 2, 3, 4, 5, 6. That's 3, and 4 and 2. That's 6. So I've got 6 carbon atoms. I'm going to count the hydrogen. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And there's going to be one over here as well. So that's 13. There's going to be one over here as well. That's 14. And then you've got 15. So let me just double check this. It's hydrogens are 15. This carbon making four bonds, four bonds. So hydrogen is 15, and oxygen, there's one oxygen. So C6, H15, and O. And O. So you had 12 hydrogens. Now you've got three more. So still not convinced. Is this 15? Let me just double check this. Is this coming out to be 15? Because only two H's are getting added, so or not. Okay, so there was no H over here. I added an extra H on this carbon atom. There is no H, so there are actually 14 H's. Not, it's not 15 H's. So let me correct that as well. So this one over here, not 15 but 14 and two H's. Now X is a mixture of two optical isomers. Draw the two optical isomers in the boxes below. So go back to X. What is X? So this carbon over here is chiral. It's bonded to four different. It's bonded to four different groups. So it's got an OH, it's got a CH3, it's got an H over here, and it's got this bunch of CH3. So this one is chiral. So I'm going to draw the chiral center. So this one has an H. I've forgotten the molecule. Just a second. So this carbon over here had an OH, it had an H, and it had a CH3, and it had a CH3, and it had a carbon which had three CH3s that were bonded to it. So you're going to just draw the three-dimensional shape around this carbon atom. The mirrored version is going to be the other enantiomer is going to be. So you mirror this molecule, and this one will have H. You'll have a CH3, and you'll have a carbon with three CH3s. So that's your other enantiomer. That's your other mirrored version of the molecule. Now both isomers of X can be dehydrated to form a single product Y. Fine. So give the reagent and conditions required for reaction number 5. So what is reaction number 5? It is dehydration. Reaction number 5 is dehydration. They gave the product as well. So what do you need for dehydration? You need Al2O3 plus heat, or you can also use concentrated H2SO4 to do that. Like if you have a look at your chart, dehydration is an alcohol turning back into an alkene. So it's Al2O3 plus heat or concentrated H2SO4. So that is what is required for dehydration. So this one they're not using Al2O3. But that is definitely they're using concentrated sulfuric acid, phosphoric acid, and heat, but not Al. But it's definitely there. I mean, if you just Google, it's definitely going to be acceptable. That's uh, maybe they're using this, but they're definitely going to be. If you look at the examiner report, then probably that would be allowed as well. Al2O3 plus heat is a dehydrating agent. Now X can form an addition polymer Z. Draw one repeat unit of Z. So we have to. I'm going to draw the repeat unit over here. So I've got this molecule. It's got a double bond. So I'm going to draw the molecule around the double bond. This double bond over here. It's got one side. There's a carbon, and it's got a bunch of CH3s, right? And the rest is all H. In the skeletal formula, they don't draw the H's. So how do you draw the repeat unit? It's just that the carbons would link up with the carbons or with the molecules next door, and the double bond in the middle would turn into that's going to turn into a single bond. That's going to be your repeat unit for the polymer. और उसके बाद है कि that's probably the last part. Reaction 6 does not proceed quickly and suggests why this is the case. So the simple answer to this is if it's a 1 mark question, it's got a high activation energy. That's about it. So whenever the reaction is not proceeding or happening, I didn't even look at reaction number 6, but its addition polymerization doesn't happen at a very fast pace. So it's got high activation energy. It needs energy for the reaction to happen. So that's about it for this. So ठीक है, Abdullah and Maruk and Saima, we're gonna do the next paper in the next class then. ठीक है, okay everyone.